Okay, we got only a few more points to cover for program correctness. Basically, last time we just briefly talked about informally what loop invariance versus loop variance really mean. So we're going to see one example to see completely how they can work in detail. And again, I also got a sample source code for you on the web, so you should really check it out and try to play with it. Okay, so that's what we went over last time. So these are just general concepts about loop variance versus loop invariance. But we'll see how they can be checked at the runtime, and also how we can prove them, how we can use them to prove the correctness of loops. That's something we'll see in just a moment. Okay, that's something we went over last time. Let's just go over this very quickly again, okay? Now, let's now try to combine these two diagrams together. So now, over here, let's review, first of all, syntactically, what do we have for loop? So we have some from, which means we're going to specify some initial statements which will be executed only once, okay? And then what it is supposed to achieve is to establish the loop invariance to begin with. So once this is done, we're going to see if the exit condition over here, which is B in general, which is a Boolean condition, if the exit condition is already false, that means, if the exit condition is already true, that means we'll not even enter the loop for the very first time. Otherwise, we can go into the loop. Every time we can go into the loop, then that means we can execute the body of the loop for one more time. And then, at the end of the loop, we also got to check something called variance. Variance is actually some integer expression which will tell you how many more iterations you will have in order to terminate, okay? It must be some finite integer, as we'll see, but we got some common pattern for you to follow, okay? And also invariance over here. So that's syntactically how a complete specification for the loop you will have. Of course, if you do this in other languages without the native support for invariance and variance, this is something you would rather want to have in your mind, so you can document your code, so you can always try to do some verification yourself of the program, okay? And this is also the thing I talk about. This is a diagram, also I went over last time. You can also refer to recording. What's really important here is you want to say that as soon as your program terminates, it's going to be some program states. States means that the combination of the program attribute values, they must satisfy three different things. Okay, over here, this is the terminating states. So terminating states, and it should really satisfy three things, 1, 2, and 3. Okay, first of all, it is not the case that the exit condition is sorry, let me say it again, beg your pardon. First of all, it must be the case that the exit condition here is true. That means we have already exited from the loop, so it must be true. That's first of all. And the second condition is the loop invariance I over here must be true as well. Okay, so it's really important that usually the combination of the exit condition together with the loop invariance can prove something about the post condition. Okay, we'll see example. And then the third thing that should be true is the post condition. Okay, in which case it's not here, but you can think of maybe you have somewhere ensure something over here, and you can say post condition, for example, R. In this case, the post condition R should be true as well, which means as soon as you terminate the loop, the post condition must be established as well. Okay, guys, any questions about syntactically what each construct over here means? So these are the things you would need in order to see if we might get any runtime assertion error, or if we may get any proof error. Okay, that's something we'll see. Okay, now let's see one complete example. Okay, let's say we have a query over here, and the query over here is going to take one parameter, which is A of type array of integer, which might be empty. For void safety, let's assume A cannot be void. Okay, that should be quite obvious, hopefully, from what you have learned so far. Okay, A can be empty or cannot be empty. And then it's simply going to return the result being the maximum of the entire array. Okay, it doesn't matter how large the array is. Let's now go over very quickly. Of course, in terms of the implementation, you know pretty well how to do it. But what's really important is to pay attention to loop invariance and variance. I'll show you, first of all, the correct version, and then help you trace the program and see why always the loop invariance can be maintained and we don't have any loop variance violation. And then I'll give you another two examples where one, the loop invariance will be wrong. Another one, the loop variance will be wrong. Okay? So you can really see how things should really work together. Okay, let's say we have a loop, we have a local loop counter I, and then let's say initially, in order to establish the loop invariant, this is what we say. We say that I should start with a dot lower. So this is just to accommodate, you may want to start your array indices with any number. It can be 0, it can be 1. So it's going to accommodate both possibilities. I is going to be a dot lower to begin with, and then let's say we're also going to assign AI to be result. Okay, just the first one. Okay. And then the invariance is as follows. Let's try to understand this predicate logic here. Okay. Over here we say for every j such that a is in between a dot lower, the minimum index you can have, and also I, which is the current value of the loop counter. Now notice that over here it's strictly less than I. Okay, notice that. Okay, I want you to pay attention to that. There's a reason for that, as we'll see. And then we say that for every such j, and then we say that result larger than or equal to aj. Okay, basically I want you to just look at one diagram which we talked about before. Loop invariant basically is like a special case for the post condition we want to establish. Let's say if eventually we want to figure out the maximum value for the entire array, for example. Now, depending on where I is, I can be, for example, anywhere as we go before we terminate. So now we want to say that somehow for the part of the array that we have scanned so far, the maximum is the current maximum as far as the part of the array that has been scanned is concerned. Okay? We'll see. Okay? So I just want you to link to this previous diagram which I illustrated before. Okay? Now how do we translate this guy over here, which is predicate logic, into programs? We can use across. Now we can see that we say across a dot lower until I minus 1. You should notice that I minus 1 here is to correspond to strictly less than I over here, right? We're saying that j can go all the way up to but excluding I, right? So that means the largest value you can get into is I minus 1. And then we say all the items from that particular sub-range we have scanned so far, all the elements should be less than or equal to the result, which is the maximum so far. Guys, any question about invariance over here? We'll see how this works in just a moment. But maybe what you really want to focus on is, given this predicate logic, can you translate that into IFO and vice versa? Okay? Either way is possible in the exam. Either way is possible. Okay. Of course, you will see different examples on different predicates. Hopefully, you will get a better feel. And then the exit condition is, as soon as I is larger than a dot upper, we're going to exit. So what does that mean? As long as I is less than or equal to a dot upper, so the last value we're going to use for I will be a dot upper. Okay, that's something you should really try to convince yourself. And then what about the body of the loop? The idea is easy. We simply say if the current element, which is AI, if the element is strictly larger than the temporary maximum, then we're going to replace the maximum. Otherwise, do nothing. And then we always increment I is assigned to I plus 1. I know many of you, well, quite a good number of you, always forgot to put I is assigned to I plus 1. Okay? Maybe that's quite an issue for IFO, but you know, in the case of Java, if you use a while loop, you can also forget about that, right? But my point is, you will see that we do have a way of formalizing this termination condition into a whole triple. That's something we'll see. Okay? It's really important. Okay. Okay, now variance. Okay. First of all, the only thing I want you to realize is variance over here is an integer expression. A dot upper, whatever it is, minus I plus 1. Tell me something here. When I say a dot upper minus I plus 1, is the value for this expression going to change between iterations? Intuitively. Which one is the variable? Which one will change? To be more precise, you can see here, this expression here contains 3 different integer expressions. We got a dot upper, we got I, also we got 1. Do they always change, or only some of them? Only I, right? A dot upper doesn't change because we don't intend to resize the array. 1 doesn't change, of course, okay? Now, another question, just to get your intuition. as we go along the loop, do you think the integer expression here keep incrementing or decrementing? Decrementing, right? Because we know that every time we just increment I, and now we got minus I over here, of course it's going to be keep decrementing. Okay, that's some intuition. So the variance at the bottom line, it should always decrement. And eventually it should decrement just down to 0. And then it's about time to exit. Okay, that's something you should really keep in mind. Okay, now finally, this is the post condition. I want you to compare two things, the red and the green over here. You can see that for all j, and then let's have a look at the green loop invariant first. Over here, j is in between a dot lower and the current counter I. To be more precise, I minus 1. However, in the red post condition over here, it's between lower and upper, right? Thinking this way. Let's just go back to the diagram here. If you think about the post condition over here, and we talk about the j over here, in the case of the post condition, the range of the array that we would like to assert about the result, how large is the result, is in between lower and upper. That's about the post condition. In the case of the loop invariance, in that case, we only asserting this sub-range, which is between lower and wherever I is. For example, if I is here, only until I minus 1. Because we know that I will keep incrementing between the iterations. So eventually, I will be incremented to a dot upper plus 1. That's when we can exit. In that case, if I is actually incremented to here, which is a dot upper plus 1. In this case, we are really considering this entire range. So in that case, logically speaking, loop invariance would just be equivalent to the post condition. Okay? So that's why I tried to emphasize last time, typically loop invariant is just a special case for the post condition. You start with some very small sub-range, possibly empty, and then between the iteration, you try to grow the range one by one. Eventually, the sub-range will just be as large as the entire array. Okay, that's something you should really, that's really the insight into the post condition and loop invariance. Okay, and then of course you can translate this into the across syntax. Okay, for that part I can leave to you. Guys, any questions until now? Of course I'm going to trace it and show you. Questions? No? Are we okay? Okay. Before I do the trace, let me just remind you once more how it's going to be the sequence of tracing. Okay, so when you review the lecture, you can also see. Okay, let's go to this code over here. Okay, let's see what's going to be the sequence. Okay, we're going to execute the initialization step for just once. And then we're going to check if the invariance, okay, let me just write a bit better. And then we're going to check if the invariance is going to be true for the very first time. If it is not, loop invariant violation. And then if the invariant is established, we're going to check if the exit condition is true or not. If it is true, that means nothing to do any further, exit. Otherwise, if B is not true, then we'll go ahead and go on. In that case, we'll go into the body of the loop and then execute it. Okay? At the end of the execution, we check several things. Again, we're going to check to see if the variant expression here is still positive. That's something we're going to check. It should always be positive. After the variant check, then we go back to the invariant check to say that after the very first iteration, is the loop invariant I maintained? It is still true. If it is still true, if it is not true, then loop invariant violation. Otherwise, if it is true, then we go ahead and evaluate the exit condition again. If it is true, exit. Otherwise, go ahead to the second iteration. Okay? Now that is at the end of each iteration, you got to check several things. First of all, you got to check the loop variance, make sure it's positive. Also, you got to check the looping variance and make sure it's maintained. Also, you got to check the exit condition to know if you want to go any further. Okay? That's about the kind of the sequence of steps for checking things over here. Okay, let's try. Okay, so I'll leave this program over here handy, and then the best way to do this is by filling up some table over here. Okay, I think only the beginning and the first or second iteration is a little bit difficult. Okay, let's try to do it together. Okay, now let's try to use this particular example over here. So let's say we have an array of size 4. Okay, now let's try to answer some question here. Okay, as you can see from the previous slides over here, the loop counter is going to be initialized to a dot lower. Okay, let's just make some assumption here. Let's say a dot lower is simply just 1, and a dot upper, in this case, is just 4. Okay, let's make that assumption. Okay, so now you can see that on a high level here, so it's going to be initialized to be a dot lower, which is going to be 1. Okay, so that means for I over here, we can have 1, 2, 3, and 4. So that means we're going to execute the body of the loop 4 times exactly. And then at the end of the 4th iteration, we're going to actually increment I from 4 to 5 again. In that case, we're going to increment that to a dot upper plus 1. In this case, you can see that the exit condition over here is going to be true. Because when I gets to a dot upper plus 1, a dot upper plus 1 is larger than a dot upper. So that means time to exit. Okay, that's the overall picture. The tricky bit is really about how the loop invariant is going to be maintained. Okay, let's try. Okay, now let's say that before we enter for the very first iteration, we're just going to initialize. Let's look at this. What's going to be the initialization step? We're going to say I is assigned to be a dot lower. Okay, let me just put aside initialization over here. So that's exactly this step I'm talking about. I'll put it here. First of all, I is assigned to a dot lower. I'll just say 1. Okay? And then I'm going to say result is assigned to A1. And then result is assigned to A1. In this case, it's simply just 20. Guys, agree? Okay? That means result is going to be 20 to begin with. And now the question is, let's just do exit condition here. Okay, now going to I is larger than a dot upper. A dot upper is always going to be 4. Okay, now is exit condition true or false in this case? False, right? Because you got 1 larger than 4, which is false. Very good. Now let's think about the loop invariance over here. Let's try to see exactly how it is going to be evaluated. And now after the initialization, this is how the loop invariant going to look like. I'm going to basically copy this line over here, except that I'm going to replace the i's value by the current value, except that. Okay, I'm going to have for every j such that a dot lower, which is 1, okay, less than or equal to j, less than I currently is 1. Okay, and then I have result, I'll say R, larger than or equal to a j. So this is the loop invariant we're going to evaluate the first time to see if that would be established by the initialization steps. Now, guys, tell me, you got everything you need. Is this predicate here going to evaluate the true or false? If true, why? If false, why not true? I'll give you a little bit hints. Focus on the range of j. And let me just put one more thing. So the result we have basically is 20, right? So now I'm going to put, let me just erase this R over here. It should be 20. Okay? Rob, go ahead. Aha, why does it not fit the range? Is there such a number? So that means there's no way you can actually satisfy this so-called empty range. Okay, that's very good. That's exactly the right first step. And now let me just ask you something from 1090 very quickly. Think about this. If I have for R, okay, X such that false, and then any predicates on X. So that means I have some empty range over here. According to what you learned before, should this be true or false or something else? True, okay. I tell you what, true is the right answer. True is correct. Okay, this should be equivalent to true. I agree. But can anybody explain to me why it should be true rather than false? Yes. Not quite, not quite. Yeah, not quite. Yes. Actually, any predicate, basically. The P of X. P can be anything. Okay, guys, let me ask you this. If I want you to prove that a universal quantification is false, how do we prove that? What does universal quantification mean? That means everything, every item in this particular collection is satisfying the property. How do I prove that the universal quantification is false? How do I prove that? You chose one witness, choose any item from the collection there, and they show me that for this particular item, it's going to dissatisfy the property, right? That's how you prove that it is false. Now, in this case, can you find any such item to prove that it is false? You cannot, right? Because false means empty. Then how can you choose anything from empty? That means there's no way you can prove that this is false. So it's got to be true. Okay? That's kind of the rationale. Okay? Okay, I will put it here. There's no way to choose a witness, let's say Y, which is a Y, such that P of Y is false. There's simply no way for you to do such a thing. So that's why it should be false. So there's no way for you to prove that it's false, so it must be true. Okay, so now, guys, any question about this? That's actually, well, I would say that's maybe one of the very few logical property you have to know for this course. Yes? P of Y, yeah, over here. Now you can see here, it's a kind of a dummy variable, right? So here, since we talk about X, so I put X over here. And now I talk about, you can choose any Y, so I put Y here. So X and Y, they're just symbolic. They can be replaced by any item. So guys, any question about this, please, before I move on? Okay, I'll see you okay. Okay, having said this, let's go back to our original question here. Right, as Rob observed, over here you can see that this is just not possible. Right? You cannot have anything that's larger than or equal to 1 and less than 1 at the same time. So this means that's simply false. So usually, the looping variant may just be established trivially. However, we'll see some cases where it may not be. Okay? So now that means this is just equivalent to true. So that means the initial looping variance is established. Guys, questions? Are we okay? That's how we see the looping variance. But now you want to see something here. So that's why I really want to draw your attention to this particular sign. The strictly less than is really, really important. As we'll see later as an exercise, if I change it to be less than or equal to, you're going to run into trouble. We'll see how. Okay, let's do maybe 2 more iterations, and I'll really leave the rest to you. So now let's say we are done with the, so now let's say up to now, so we know that the exit condition is false. That means we are going to go into the loop for the very first iteration. Okay, now, what is it going to do? It's simply going to say, now if A1 is larger than result, remember we initialized the result to be A1. So A1 larger than A1 is going to be false. That means we don't have to update the maximum. And then we'll simply just increment I from 1 to 2. Okay? So now you can see that now I is equal to 2. Okay? So now, before I show you the looping variant in just moments, now we have to calculate the loop variance over here after every iteration. Now, what would be the loop variance over here? Well, think about it. It's going to be a dot upper minus I plus 1. It's going to be 4 minus 2 plus 1, which is 3. So what does that mean? That means at the end of the first iteration, we got 3 more iterations to go. Okay? So 3 over here means at the end of first iteration, 3 more to go. Okay, as we'll see that's something I will leave to you. You will see that the loop variance at the end of each iteration is going to decrement just by 1 because I is going to be incremented by 1, right? So you're going to see 3, 2, 1, and 0 eventually. Why eventually 0? Because when we exit from the loop, that means I is strictly larger than a dot upper, which is a dot upper plus 1. Now, when you try to apply this into this, a dot upper minus I plus 1 is the loop variance. Now, if I happens to be a dot upper plus 1, if you apply it, you will see exactly 0. Okay? Now, we know that, guys, any questions? Okay? As you can see, tracing this is quite sophisticated. I just want to give you some idea. You should really try to do this, because if I give you any arbitrary looping variance, I may simply ask you, is this looping variance okay? If you don't think that's okay, tell me why. Okay? And how do you tell me why? Well, trace it. You don't have to do this much detail tracing table, but you got to tell me exactly how the looping variance is going to fail. Okay? Okay, let's do one more. Okay? And now, at the end of the first iteration there, we know that we are basically, okay, this, at the end of the first iteration, we are not going to replace a maximum by anything, right? It stays as 20. So it's still going to be 20. Now, the only thing we will change is, let me just write it here, okay? Now, what about the looping variance over here? I'm going to write it right here. It's going to be for every j such that a dot lower less than or equal to j, and less than, in this case, I would be just 2. And then we have result larger than or equal to, result stays to be 20, larger than or equal to a, j. In this case, do you think it is true or false? Again, I would say this is really the key. Now, we don't have empty range anymore, do we? Now, what's going to be the valid indices of j to be considered? Only just 1, right? Okay, you can see that the only valid index will be just 1. In this case, what we will have is j is just equal to 1. In that case, do we have 20 larger than or equal to a1? We do. Okay, so the looping variance is maintained. Okay, as you grow the as you grow the index for I, you're going to see that it's going to be maintained throughout the iteration. Okay, that's how you should trace. Okay. Guys, any questions or you need more? You want me to repeat something? Are we okay? Okay, maybe there's something you should really try. Okay, now to really help you understand more, this is what I would say. Okay, you will see the complete table over here. So this is the case where both the looping variance, the green one, and also loop variance, they are both good. Okay, now let me just show you one more example here. Now the only thing I changed was I have less than or equal to I. That's the only thing I changed. Okay, now I'm just going to show you something very quickly over here. So now in this version here, the only thing I changed was it's now less than or equal to I. However, it's going to throw some loop invariance violation. Okay, now let me just show you directly what the result is, and then something I'll leave to you. It turns out if you got this wrong looping variance over here, you're going to have some loop invariant violation at the end of the third iteration. Okay, let's see why. Okay, I'll give you some idea verbally. That's something you should really try to figure out. Okay, thinking this way. At the end of the second iteration, we know that the loop counter I is going to be 3. Okay, first of all, that means we're going to replace the I over here by 3. Okay, so that means a dot lower, which is 1, 1 less than or equal to j, less than or equal to 3. Now, what are the valid indices for j? 1, 2, and 3. 1, 2, and 3. Okay, remember, that's the trick, because we actually replace this by less than or equal to, right? Okay, now it's going to be 1, 2, and 3. Now you can see that result currently is still 20. We haven't replaced them yet. So now, if you got 1, 2, and 3, what does that mean? That means every element from indices 1, 2, and 3 are going to be smaller than or equal to the temporary maximum. But is that the case though? It is not, because you can see at index 3 over here is 40. That's exactly what's going to come in the coming iteration, but we haven't done that yet. That's why you must have the less than sign over here. Okay, guys, that's a very quick intuition of what you should do. Okay. Questions about this? So in this case, you will see that exactly at the end of the second iteration, you're going to have this trouble here. Okay. So if I give you a question like this, I might just give you the entire loop, and then with the wrong looping variance. And then I say, now show me that, you don't have to prove, but tell me if there's going to be anything wrong when you try to execute on this particular array of size 4. If there is, show me exactly how the looping variant violation is going to occur. Okay? Okay, good. I'll move on. So that's the second example here. And the third example, I changed the looping variant back to the good one. Okay, I changed back to the strictly less than. But now, the thing I put as a bad version is a loop variance. So now, rather than having a dot upper minus I plus 1, I remove the plus 1. Okay, that means the loop variance is going to be 1 off from the previous one. Okay, so if you try to trace it, you will see that we're going to start with 2 rather than 3. If you compare it with the previous table, 2, 1, 0, and then when we exit from the loop, which means I is exactly 5. If you say a dot upper minus 5, you get minus 1. So this is not good. That means because as soon as you exit from the loop variance must be exactly 0. That's why I said in the very beginning, abstractly speaking, the value for loop variance currently tells me how many more iterations there should be, is required to do. Yes. Oh, good. So the question was, good question. The question was, let me just use some diagram to show you. Give me one moment. The question was, what's the difference between the loop variance over here, which is an integer expression, versus the exit condition? Oh, thank you. What's the big difference between these two? Okay. So now, what's the difference between variance over here, which is v, and also the until, which is exit condition for, which is b, right? First of all, this is a Boolean condition. And this one here is an integer. I would say they are somehow connected. They're somehow connected because when you see the proof obligations the whole triple for proving the correctness of loop, you will see that they are connected. But let me just state that right now. First of all, the b over here, that means as soon as b is true, that means more iterations to go. Because we don't have to exit yet. Okay? Oh, as long as this is, beg your pardon. As long as this is not true, as long as this is false, that means we don't have to exit yet. That means we should really have more iterations. Okay? And now, as long as we don't actually have to exit, so what does that mean? That means the loop variance v must be strictly larger than 0. Okay, and now as soon as the exit condition becomes true, that means now it's time to exit. In that case, v should just go to 0 exactly. Okay, so now if you see that in the previous example there, 1.1, you'll see that over here. Now, okay, how about this? You can see now, let's try to see these two columns. Exit over here and also loop variance. Let's see that, right? You can see now, As long as the exit condition is not true, that means we don't have to exit just yet. In that case, the loop variant is always positive. Okay? Now, as soon as the exit condition becomes true, that means now it's time to exit. Now, loop variance must be 0. So that's the correlation. Again, the exit condition and loop variant, they work together to make sure your loop terminates. Okay? Your loop cannot just go forever. Not acceptable. Okay. So now, guys, any questions before I give you some exercise to do? Okay, now the exercise is as follows. I want you to consider something very similar to what you did in the lab and also in the lab test. Okay, let's say we got dictionary, we got values and keys, and let's say we got a model, just function. Okay, and then let's say we got a feature called get keys over here. It's going to return some iterable. Okay, you can do something over here. Now I want you to think about what the looping variant should be. I want you to come up with both the predicate logic and also the IFO syntax. Okay, just something that's executable. So now, at the same time, this is also the solution to one of your lab test questions. Remember, there was for the get keys, we got 2 post condition, right? So we got result valid and also no missing keys. So these are the 2 things I will leave you to study a bit. Okay, basically what these 2 post condition are doing is as follows. Okay. Okay, now, in general, how do we prove that 2 sets are the same? Okay, 2 sets are the same if S is a subset of T and also T is a subset of S. Okay, now think about how we can transfer this concept into the get keys over here. Okay, let's think about this. You can think about get keys is going to return a set, iterable set. Okay, let's. Okay, now let's say S and T. Let's think about if S is simply something like the return iterable set of keys whose associated value are simply just V. Okay, you can see that that feature there takes V as a parameter, right? Now, what about the other one? The other one somehow is if you try to do range restriction. Okay, the model of dictionary, which is a function with its range restricted to V. Okay, because we want to make sure we get all the keys where we simply got V being the range value, right? So now we want to make sure these 2 concepts over here actually match. Okay, we want to say somehow whatever that's in this set over here is a member of this set and vice versa. Okay, that's something you will see in this predicate over here, right? For example, let's say over here you can say for every key K such that K is a member of the iterable set. It's a member there, so you can do a cross. And then if you try to use model to query about the value for the key, it should be V. Okay, that's one way. Let's go the other way. The other way means for every key in the model that has the associated value being V, it must be included in the result. Okay, that's something I'll put it here. However, to really translate the no missing keys into a cross syntax, it takes a little trick. Okay, that's something I'll leave to you to figure out. So that'll be your exercise. Figure this out and then try to see how you can write a looping variance in both the predicate logic and also programming syntax. Of course, if I ask you this question in the exam, so when I say write invalid IFO syntax, I can tolerate some typing error, that's okay. But cannot be too far away, right? Okay, now finally, let's try to see, so now that we talk about loop invariant and loop variance, now how do we prove the correctness of a loop? Okay, for example, let's say this. We start with some precondition Q, we start with some precondition, and then we try to say doing some initialization step for the loop, and then we have invariance I, and then we have to say as soon as B is true, we're gonna exit. And then we're gonna keep repeating the body of the loop as long as the exit condition is not true. And then we have the variance over here to say as soon as we actually exit from the loop, it's gonna be 0, things like that. And then at the end of the loop, we also want to make sure the post condition R is established. So now let's say in general, if we got such a problem to solve or to prove, how would you prove it? It turns out to prove this is rather sophisticated, but I'm going to go over each one of them with you. And I will also give you some exercise to complete by the exam. So now let's talk about partially correct. So the way we're going to prove about correctness of a loop, we're going to separate between two things. One is about termination. The other one is assuming that termination is the case, and are we going to establish the post condition at the end? So these are the two parts. Okay, let's talk about partial correctness first. Let's not worry about termination just yet. It's a separate proof. We're going to say that, of course, first of all, in this slide, I'm going to say informally in English. And let's see how we can formalize this English into Hoare triples. And that's something you got to prove. Let's try that. So let's say we start with the precondition Q. We want to make sure after executing the initial step, we can establish the looping variance. That's the first thing. You want to make sure at least we got some looping variance being true to begin with. Okay? That's the first one. And the second one, we want to make sure as long as we are not ready to exit yet, at the end of each iteration, we got to maintain the looping variance. The looping variance should never be violated. Okay? That's the second thing. And now let's say we are now ready to exit. Given that the looping variance has been maintained, then that means now we must have established the post condition. Otherwise, you're really terminating in an illegal state. You want to make sure whatever state you terminate must be a state that satisfies the post condition. Okay, that's number 3. Okay, that's just informally speaking, right? Now, how do we prove about termination? There are two things. Basically, we want to make sure the loop variance expression over here is going to stay positive as long as we are not yet ready to exit. And then every time at the end of the iteration, we're going to decrement the value. Okay? So first of all, it stays positive, and also it's keep decrementing. Again, so these are simply English descriptions. Let's see exactly how these can be translated into logic. So once you see the Hoare triples there, you can just go with the rules that we talked about so far. Okay? Let's see. Let's say again, we have some precondition here to start with, and eventually, upon the termination of the loop, we want to establish the post condition. Okay, that's just a one-line definition for your loop. Okay. Now we say that it's part. Let's just repeat the sentence, and I'll show you how you can formalize it. First of all, we want to make sure the initialization step is going to establish the looping variance. How do we do that? So this is a Hoare triple. Given the precondition Q, execute the initialization step, and then we'll establish the invariance. Right? Hopefully that's clear to you. Okay? And second one, at the end of the body, if we are not ready to exit, but at least the looping variance must be maintained. In this case, you can see now the precondition is, given that the looping variance has been maintained from the previous iterations, and then we are not ready yet to exit, that's why not B. So that's the entire precondition for each iteration step, right? And then once you execute the body of the iteration, you want to maintain the looping variance. So one interesting thing to see is you see looping variance I occurs both here and here. Assuming that it is true, we want to make sure it's still true at the end of the iteration. Okay? Okay, final one. Now let's say we are ready to exit. We are ready to exit, that means not B. And also given that the looping variance has been maintained, which means I. So what does that mean? That should logically imply the post condition is established. So this one is not really a Hoare triple, it's just a simple implication. Given that the looping variance is true, and also the exit condition is true. That implies the post condition must be established. Okay? Now, what about termination? Termination, first of all, we want to make sure as long as we are not exiting, the value must be positive. That means, given that we got invariance always maintained, also we are not ready to exit just yet. And then if you try to execute the body of the loop, you want to make sure it somehow is going to maintain the variant expression being positive, strictly positive. Okay? Finally, you want to make sure also the loop body is going to decrement exactly, it's going to decrement the loop variance by some value. Okay? That's why you'll see this. Okay, again, the looping variance is assumed, and also we are not ready to exit just yet. And then you want to make sure after executing the body of the loop, you got the, okay, let's see V versus V0. V0 is like an old V0, like old V in iPhone. So we want to make sure the new value at the end of the current iteration is strictly less than the value in the previous iteration. Okay, that's why we have this strict inequality over here. Guys, any questions? It's a bit abstract, I know, but I got an example for you. Just next slide. That will also tell you what your assigned exercises are. Yes? So, oh, I see what you mean. So the question was, what should be the order of proving these? I would say it's up to you. It's completely separate. You can either try to prove termination and then partial correctness or the other way. Doesn't matter. But eventually you must prove both. Okay? Good. Okay, now guys, this is your exercise. Let's say this is something I give to you in the exam. I'll give you this group, this code over here. It's completely valid program, except that for the looping variance, for the looping variant and the post condition, I simply use predicate logic to make it easier for you to prove. Okay? Now let's say given this, question is this correct or not? Okay? So how do you go about doing it? Okay? Now, the idea is very similar to what we did before. Basically, you want to translate this program over here into different Hort triples, the 5 of them, which I mentioned in the previous slides. Okay? I'll show you exactly how they should look like, and then I'll leave the proof to you. So that'll be exercise for you before the exam. I'll give you some sample solution, maybe about 1 or 2 days before the exam. I really want you to try. Don't wait my solution to come. Okay? Okay, so now you want to prove that each of the following Hort triples, which we mentioned in the previous slide, should be true. So now, first of all, we want to make sure the looping variant is established. So now, since for that particular program there, we have no require. So precondition is simply just true. Okay, we have true over here, and then that's the initialization step. It's a sequential composition of 2 simple assignments. And then we want to make sure it establishes the looping variance. Okay, first one. And then how do we make sure the looping variance is maintained? In that case, starting with the looping variance being true, and also the exit condition is not true, which means we are not ready to exit just yet. And then you execute the body of the loop, which is going to be if then else, followed by some increments. And this is going to maintain the looping variance. Okay? Number 3. You want to make sure now if we are ready to exit, that means given that the looping variant has been maintained, the post condition must be established. Okay, given that the looping variant has been maintained and the exit condition is actually, beg your pardon, that's a typo. I'll fix this. This should be I larger than upper. Okay, I would fix that. Given that the looping variant is true, and also the exit condition is also true, that means the post condition must be established. Okay, I'll definitely fix this, otherwise you cannot prove it. So this one over here, it should be I larger than A dot upper. There's no negation there. Okay, I'll fix that. And then number 4. Now here it's about the termination proof. Okay, now we want to make sure that given that looping variance is maintained, and also we are not ready to exit just yet, and then we execute the body of the loop, we want to make sure that the loop variance stays positive. Okay, you can see this is the expression for loop variance. Okay, finally, we want to make sure the loop variance keep decrementing. Okay, how can we do that? Again, Given the loop invariant and given that we are not ready to exit just yet, now execute the body of the loop. Now what we have is, we can say a dot upper minus I plus 1. This one is the current evaluation. And then conceptually you can think of, you say old this expression over here, right? That's why I put 0. But to be easier for you to prove, you can think of, if you apply old over here, that means apply the old to every variable over here. That means you got a dot upper 0, I 0, and 1, right? But now since we know that a dot upper never changes, so you can just say a dot upper minus I 0 plus 1. Okay? Just a little trick to show you. So that's your exercise before the exam. You want to prove each one of the 5. Okay? Of course, form a group. Don't try to just do it by yourself. You want to discuss. Okay? We can drop by my office hour either this week or next week. Okay, now, when you are proving, when you're trying to prove, do the proof for the exercise, you might run into some, so these two tips will actually help you. I'll just go over them with you very quickly, but you will find you'll appreciate them more when you get stuck. Okay? So now let's say this. If I want to prove the right-hand side, I given the precondition Q and P, executing S, and then I want to establish R. Sometimes you might find that not all the preconditions here are useful. You may want to say, I only want to use Q, or I only want to use P. You will see that when you try to discharge some of the expressions in the previous slide. So I want to basically, if you want to prove something like this on the right-hand side, it would be sufficient if you simply take out one of the preconditions. That'll be okay. Okay? I'll leave the rest to you because you will only appreciate this rule when you get there. Okay? And if you're, so this proof here is optional. If you're interested in seeing how this can be proved, go ahead. Okay, tip number 2. So now you will see that because this particular program here makes use of array indexing. So you will see that every time when you have array indexing, that means index you're using, for example, I, the loop counter. You want to make sure I is always a valid index. Otherwise, you run into the array index out of bound exception in the Java sense, right? Or the array index either too small or too large, precondition violation. So I'll give you an example here. Let's say this. If somehow you want to calculate a precondition for this thing over here, because I know that eventually I'm going to evaluate AI over here. So that means I should really augment. I want to strengthen this postcondition a little bit. What I really meant by this is I should be a valid index, right? That's something you should really augment by yourself. Okay? Similarly, let's say I try to do something in the implementation here. I'm trying to use the indexing I over here. So now that means I should also strengthen the corresponding postcondition here by saying I should be valid. Okay? Like that. Okay, again, so these tips, you will only find useful when you really get into the proof. Okay? Okay, guys, any question about this lecture here before I move on to wrap up very quickly for the course? Are we okay? Okay? Yeah, give me 20 seconds and then I'll wrap it up. It only take a few minutes to wrap up, so it wouldn't take long. And then we got 2 more things to do for the course. Okay. Okay, basically, I just want to mention the important topics that you have learned so far in the course. Okay, so let's see what kind of design principle we learned so far. I just named a number of them. Okay, you should really know. First of all, I think the number 1 important technique we learned is about abstraction. Abstraction. What does abstraction really mean? That means you want to think above the code level. You don't want to just go directly to coding right away. So what you should really try to do is think about contracts, think about architecture, client supplier, inheritance, and also you want to think in terms of math models. That's why we introduced that, in the course to help you think abstractly. Abstraction is number 1 principle. Okay? You might be wondering, well, if the language like in Java, they don't support contracts natively, they don't support math models, what should I do? I do have some little tip for you. You can try to follow, maybe in the second slide. And also information hiding. This is also important. Actually, information hiding also linked with single choice principle. You want to make sure your design is such that whenever you want to introduce a change, you're only going to change in one single place, and it's not going to affect other clients, right? That's kind of, you should really try to review where we talk about information hiding and single choice principle. Okay, so these are really important. And actually, quite a good number of you actually sent email to me about the project saying, if I do such design, it seems like I violated the single choice principle. That's why I was very happy to see those emails. That means you are really thinking about your design. That's good. Okay. So always think about information hiding and single choice principle. Open close principle. Also, whenever you have your system, think about which part is going to be stable, never going to change, and which part is going to be open to extension, especially when we talk about visitor pattern. Uniform access principle, okay, we also talk about it, okay? And then we also talk about design patterns. I certainly didn't give you an exhaustive list for the design patterns, but you can definitely try to study more beyond this course. But at least these are what we learned so far, especially state, composite, visitor. I think these are the common ones. Observer, also event-driven design, right? Also undo, redo, and command, which we practiced quite a bit in lab number 4. And also for the projects, we got a separation between model and also the user interface, right? That's model view controller patterns. So these are at least what I hope you can take away from the course. Okay, that's what I hope. Now, second one, what about beyond this course? What should you do? So now, let's say, what if my program, let's say I go back to Java, go back to C#, they don't really have the design by contract natively, like require in short. So what should I do? If I were you, the best I could do would be I should document my contracts in a way. For example, let's say you got Java doc, right? You can definitely put some precondition, postcondition there. But of course, the catch is there's no runtime assertion checking for you anymore, right? Once you put a precondition and postcondition. I understand that. So the best thing you can do is to make sure two things. First of all, you want to make sure every time you change your code, if you want, you also have to review your pre and post condition to see if they should be changed as well, to make sure they're in sync. And also, the best way you can make sure they're in sync, write some tests. So the best way for you to incorporate the contract into your code, into your projects, is by writing tests. Write a test to test for precondition and test for postcondition. Okay? It's very general tips, but that's something you should really try to find out a way so that you really don't abandon these ideas, for design by contracts. What if they don't have math library, right? Similar concept. You should want to somehow to think. So again, you really want to think above the code level. So the mathematical library we don't have that many classes over there. So the one I think that's the most useful is the one for your lab test, which is relation. Mathematical relation is very similar to a graph data structure. As you learned from 2011, we say that the graph is the most general data structure for any developments. Similarly, for any development you're going to have later on, you can definitely model that using a relation. There shouldn't be any trouble. So now that means before you go into your coding, you want to think a little bit more abstractly. Think about how operations can be done using the relational operations. And then you think about how to implement them in an efficient way. Okay? Okay, now, and again, you can also use your contracts, right? To document your contract in terms of math model. Okay, also you got a test, right? Okay, one more advice for you. For those of you who want to have a good reference for software design, I do have one recommendation, okay? Nothing to do with iPhone, okay? There is a book called Software Fundamentals. So this is not really a single author book, it's actually a collection of papers. So this book here actually talks about many good software engineering principles over there. And as we'll see, the papers there are actually somehow very date back to maybe 1980s or even 70s. But those are the principles which will persist. So I would suggest check it out in the library, and then you can read them, okay, or just apply them. Especially, there's something that we wouldn't get a chance to talk about. It's something called tabular expressions. If you want to learn more about this, take 4312, requirements engineering. They're going to talk about tabular expressions. That's also a very good technique for you to design. Yes, also information hiding as well. Okay, do we have any questions about the course contents? Are we okay? Okay. Let me